Hello everybody, welcome to ENGM 2032, Introduction to Probability and Statistics. My name is Gordon Fenton. I'm going to be lecturing you this term and hopefully guiding you through this particular course. As you know, of course, this fall, the courses are online due to the COVID-19 pandemic. Where the smallest of creatures brings the mightiest of empires to its knees. And unfortunately, this means that your university education isn't what it really should be for you. And it certainly is a big change also for me. I don't know if you can see my setup here, but basically I've got a camera, which is that thing, connected to a laptop, which is this thing, and a microphone over here. And when I'm done recording, I will have to edit the recording and post it online. And there's a fair number of leaps to jump through, hoops to jump through. So I probably won't be doing a whole lot of actual editing, which is to say, if I misspeak in the middle of a video, I'm probably not going to go in and splice in the correct word. I'll probably have to put in if there's mistakes, and certainly if any of you notice mistakes, please let me know. I'll just put a post in errata or something like that, maybe weekly. The biggest challenge in this course is really going to be for you as students. Learning online requires a lot of self-discipline, I think. What I might be tempted to suggest is that you put aside the hours that are normally would have been in-person lectures and use those hours to actually take a look at these videos that I'm going to be posting and do the work for this course. If you do that, then you're pretty well on track as far as the time is commitment is required, and it is a way of organizing your time so that you can share it between the 5 or 6 courses that you happen to be taking this year. The other thing is we're going to go a little bit different this year. I'm going to post 10 assignments. Oh, I'll go through the course outline in a minute, but the assignments are primarily for your practice. Learning, well, any course really, but certainly probability and statistics is much like learning how to play the piano. You will never learn to play piano by listening to somebody else playing it. You've got to actually struggle with it yourself. And so the assignments and the practice problems that I'll post online are there for your so that you can learn the course by struggling with the problems and learning as you go along. There will be a temptation to search online for solutions. If you're really running out of steam, you can do that, but again, if you don't struggle with this yourself, you're not going to learn it. And to be fair, you're paying in the order of $10,000 to $20,000 a year for your education. You might as well get your money's worth, and that means struggling with this yourself and learning the content. If you make your way through a course without learning it, you're going to have to learn it sooner or later anyhow. Particularly if you end up at the end of the year and haven't learned anything, you're going to fail the following year, or at least when you get out in the working world. And then, in order to learn this stuff, you just got to go back and do it again. So it basically means that your $10,000 to $20,000 a year has been just wasted entirely. So you have to be somewhat honorable, ethical, and self-disciplined, so make sure that you put the effort into this course that is required to properly learn it as you go along. Just remember that this is your education. It's not mine. You're the one that benefits from this. and you don't want to do it all over again. Regarding a textbook for this course, there are a number of good textbooks, and I'll mention that when we go over the course outline. And I found a number of free online textbooks that we will post on our website that you can make use of. I think the plan is to post the lectures as videos. That's what I'm giving right now, but conduct the tutorial in real time online. So the tutorial will be your chance to ask questions. There'll be myself and Laura Luna helping you do the tutorials, and we'll set up a discussion board for you to ask your questions. Perhaps we'll have questions in some other format, I'm not sure, but it could be audio or even video. The rationale here is that the lectures are largely delivery, so they will be posted as videos. But the tutorials are intended to kind of help you with your personal questions about the course. Okay, well, with perhaps no further ado, I'm going to switch over and let's start. Oh, well, basically I want to talk about why we need probability and statistics. So I'm going to bring up a little set of slides here. If you take a look at the way engineering operates, it's basically a balance between three things: utility, cost, and reliability. Utility is usually specified by who your employer is. They say, okay, well, I want a calculator that does this, and I want a computer that does this, or a building that has certain square footage, and so on and so forth. So that's usually as utility is specified by the employer. But you basically have control over cost and reliability. And so we know, for example, here's the first slide here, is the Egyptian pyramids were designed to have an extremely high reliability. Even after 5,000 years, a lot of those pyramids are still in excellent shape. And not surprisingly, they're just made out of great big blocks of stone. So basically the utility there was to provide a burial room for an individual, or perhaps his or her family. But the cost of providing that utility was staggering. In today's dollars, it would be about $5 billion to construct one of those pyramids. But the other side of it is that they last for a long, long time. The probability of failure of those things is extremely small. So the balance there was to say, okay, well, I'm going to spend a lot of money to get a very, very small probability of failure. Well, we can't afford to do that these days. We have to be a little bit more practical. So we want to balance cost versus reliability in a more organized fashion. Let me just try page down. Okay. So we try to produce designs now that are reasonably safe, but which don't cost an arm and a leg. But we have to be a little bit careful with this because, for example, the National Palace in Haiti looks grand, but the probability of failure due to an earthquake was far too high. So they didn't spend their money on the right aspects of the design of this particular structure. And in fact, in an earthquake of magnitude 7.0, which is not, it's a reasonably sized earthquake, but it's not huge, the palace was completely destroyed. So all of the money that they spent on the looks of the place came to nothing. They needed to spend some more money on the actual reinforcement required to increase its reliability against earthquake loading. So, like I said, there's this balance between failure probability and cost. The cost is on the horizontal axis here, and failure probability on the vertical axis. As we move down the vertical axis, the failure probability goes down. So we get safer and safer structures as we go down. The pyramids would be way down towards the lower right-hand corner of this, basically very high cost, very low probability of failure. The palace would be reasonable cost, but a much higher probability of failure. So as I mentioned, engineering design involves a trade-off between cost or value and failure probability. And the general rule is that the lower the failure probability, the higher the cost. So depending on your budget, you want to aim for as high reliability as you can for perhaps a fixed cost. And that really is what defines an engineer, and in fact gives an engineer their value to society. Sorry about it. Their value to society. If you can do a good job at balancing failure probability and cost, then you are quite valuable to society, and you will reap the benefits in your career. In general, acceptable failure probabilities are dictated by social norms. This isn't true of all areas of engineering, but a lot of areas of engineering, certainly civil engineering. The required reliability of bridges and buildings and so on and so forth are dictated by governments and society. But it's also true of safety standards in automobiles and well, basically lots of other things that engineers are involved with. Let's go to the next slide. So I am chair of the Foundations and Geotechnical Systems Committee of the Canadian Highway Bridge Design Code, CHBDC. And this is basically what I do on that. I develop reliability-based design code provisions for bridges in Canada to optimize the balance between reliability and cost. So we've got, for example, the picture just before was the Confederation Bridge over the PEI. It had a cost of $1.3 billion and has a design lifetime of 100 years. So basically it means that it's targeted at surviving for at least 100 years. It probably will survive longer than that, particularly if we maintain it properly. Basically the idea is that in that 100 years the probability of failure is relatively small, something in the order of 1 in 1,000. Nevertheless, that bridge there's no way it's going to last 5,000 years. It'll maybe, if we're lucky, a couple of 100 years, and then we'll replace it. Small changes in the target failure probability can make large changes in cost. Good estimates of reliability are therefore critical to cost-efficient designs. And the bottom line is, if your design can save 1%, even 1% of the total cost, and still achieve target reliabilities, then you are worth, for that Confederation Bridge, $13 million. That's a lot of money. And somebody's going to be very happy if you save them that sort of money. How is the target reliability achieved for this bridge? Well, the approach used in civil engineering is the load and resistance factor design that basically thinks of there being loads on the structure that are random with time. We don't know what the loads are going to be precisely in the next 100 years, although we have some sort of an idea. There'll be loads such as traffic loads, of course, snow loads, wind loads, but there's also loads due to ice coming in along along the ocean, particularly big ice chunks or icebergs, for that matter, hitting the piers. There's also loads if a ship comes along and happens to smash into one of the piers. I'll show you a picture of that shortly. And basically, on the other hand, on the other side is the resistance of the side of the equation. That is, what is the resistance of the concrete piers that we're building? What is the resistance of the slabs and the concrete decks that we're going to produce, and in fact the foundations. These things are all random, particularly in terms of time. Anybody that's looked at a bridge in Halifax recently knows that after 50 to 75 years, those bridges don't look that great. There's often a fair amount of corrosion taking place, and we know that the strength is degrading. So we have to start looking at them fairly carefully to make sure that they still achieve their target reliability levels. So the idea here in the load and resistance factor design is that there's some sort of, on the left-hand side in yellow here, there's some sort of ultimate resistance R that we factor to at least be greater than or equal to sum of factored loads on the system. Because basically if the load exceeds the resistance, then the system fails. And so what we want to do is figure out what must those factors be to achieve a certain probability of failure in our designs. Oops. Well, the probability of failure part of it, we're now starting to talk about our uncertainty in loads and resistances. Loads will have some sort of a distribution that is random, and I'm showing that in a red curve here. It basically means that the load could be 10, or it could be 15, or it could be 20, it could be 5. And basically the relative likelihood of taking on any of those values is given by the height of this curve. So the most likely load on this system is somewhere around 8, for example. But we could occasionally get a load that's up to 20. And then on the resistance side, we've got another distribution that basically says, okay, well, our most likely resistance is somewhere around 23, 24 here. But we could have resistances that are as low as 15. And if in the lifetime of this system, the load, I might have said load here, but this blue curve is resistance. If the load happens to be 20 sometime in the lifetime, and at the same time the resistance is 15, then this system will fail. And we want to make sure that the probability of that is as low as we can make it for the cost or the amount of money that we have. One of the sort of standard approaches, traditional approaches to design in the past has been to establish a factor of safety in the design approach. So there we're saying that the mean resistance divided by the mean load is sufficiently high. So here I've got a resistance distribution with a mean of about 24, and a load distribution with a mean of 10. And here the factor of safety then is 24 over 10, which is 2.4. However, if the distributions, or if our uncertainty is a lot wider, and we see this in the bottom plot here, our distribution of load is a lot wider. That means we've got a lot more uncertainty. Then the probability of the resistance being below the load is a lot higher. So the top one has a probability of failure of around 2 in 10,000. And the bottom one has a probability of failure of around 7 in 100. So 400 times less safe in the bottom, even though the ratio of the means, 24 over 10, are the same in both pictures. So we have to actually take into account these distributions in order to figure out what is the probability of failure. So basically, how do we achieve good engineering designs? Basically, we need to look at probability theory in order to obtain the distributions of these loads and resistances and figuring out what is the probability of failure. We must be able to estimate these failure probabilities and their costs in order to arrive at designs which are valuable to our clients. And of course, this course, of course, concentrates on the probability theory side because the costs will change by the time you get out. And usually costs is just a matter of looking up what is the cost of this part versus this part in a book at some point in the future. Okay, that's that for that show. Escape to exit. Okay, well, maybe before I finish this lecture, the last thing we should look at is, where is it now? Here we go. Our course outline. So this is ENGM 2032, Applied Probability and Statistics. As I mentioned, I'm Gordon Fenton, and the tutorials will be handled by Ms. Laura Luna. And of course, we're all online, so if you want to talk to us, you're going to have to email us, and we'll set up a meeting, or like a Teams meeting or something like that, or we can try to settle things by email. Our nominal lecture times are Tuesday, Thursday, 8:30 to 10, and these times are all Atlantic Standard Time, or Atlantic Time, whatever we are in right now. What I will do is post these lectures on Brightspace probably the night before each lecture, and then you can read them over. As I said, probably a good idea to plan on spending that hour, hour and a half on Tuesday and Thursday mornings, reviewing the lecture notes and trying some problems and seeing if you have any questions, you can ask us about it. The in-person real-time lecture will be the tutorial, and that will be Wednesday, 12:30 to 2:30 Atlantic time, and that will be conducted on Brightspace. I'm not 100% sure right now how we're going to do this. We're close to 300 students in this course, so we might have to break the tutorial up into parts and have some online rooms where we can answer individual questions as we go along. But I would imagine that the first part of the tutorial would be Laura demonstrating some example problems that are similar to the assignment problems, and then the second part of the tutorial would be addressing individual questions. Okay, so the course is intended to provide an introduction to the language, logic, and math probability and statistics as used in engineering. So this is the whole idea behind how do we figure out probabilities of failure, for example. I guess you can read the rest of that. There, as I mentioned, we're going to have 10 assignments. I'm going to make the assignments, well, yeah, they're going to be due at the start of the lectures on the dates noted later on in this course outline, unless otherwise arranged with the class. The assignments, like I said, are primarily aimed at giving you practice for the course. And what I would suggest is you work through, of course, all of the problems that you can. And but I'm only going to mark 2 randomly selected questions on each assignment. The remainder you should mark yourself by comparing your work against the posted solutions, and I'll post the solutions right after the assignment is due. Let's see, we're going to have 5 take-home quizzes or tests. Each of those will have a 24-hour duration, and the dates are noted below. If you miss a test, you have to fill out a student absent reporting procedure to request accommodation for the missed test. If the request is approved by the associate dean, then suitable accommodations will apply. Otherwise, a mark of 0 will be recorded for the test. Now, we're going to be fairly vigilant about cheating. Like I said, this course is intended for your benefit, but sometimes it's very tempting to try to cheat. So we're going to be monitoring some of the common websites that people post questions and answers. We're going to be taking steps to ensure that cheating does not take place, and that that you have the opportunity to properly learn this course by practicing and by writing the test to see how you're doing. The tests are not intended to be to penalize you. They are intended to let you know how you're doing. And so if you do badly on a test, it doesn't mean that you're a bad student or anything like that. It just means that that's where you have to put some more effort. Okay, so it's a feedback mechanism for your own benefit. Student absence reporting. There's forms for that on the website. By the way, the website Course Outline has links to all of these forms. This is just the PDF version. As I mentioned, there are going to be 5 tests, and the dates and times of these tests are given here. And as I mentioned, these dates and times are all Atlantic Standard Time, or Atlantic Daylight, whatever we happen to be in right now. So just make sure, if you're in a different time zone, that you know when this starts and stops. In particular, when it stops, because when it stops is when the Brightspace is going to be cut off. So you're going to see the quiz, and you're going to write on a piece of paper or on your tablet, as the case may be, your solution, and then you're going to submit that back to Brightspace. And you have to do that before 10 a.m. on the following day, according to this schedule here, 10 a.m. Atlantic time. Assignments schedule is given there, and as I mentioned, 10 assignments. Course assessment, I'm going to give 10% value to the assignments. That means they're worth about 1% each. So if you don't get a great mark in an assignment, it's not a big deal. The main value, as I mentioned in an assignment, is in its practice. You'll more than make up the value of that assignment by doing well in the tests. The first test I put a little bit lower weight because sometimes it takes a little while to get used to how things are going, how to write a test in probability and statistics. But tests 1, 2, and 3 are going to be a little bit shorter. They're basically all aimed at 2 assignments each. So test 1 is on assignment 1 and 2. Assignment 1 and 2 are typically a little bit simpler. Then test 2 is on assignment 3 and 4, and those are starting to get into some more harder concepts, so I've given 15% there. Test 3, same sort of thing, 15% for that. And then the final 2 tests, I'm going to make them a little bit longer to sort of be a little bit broader in scope, and so I've given them 25% each value. Textbooks, as I mentioned, I'll provide links to several freely available online textbooks that are open source. So there's no, what's the word I'm looking for, liability issues with respect to copyright. I've also put out some other textbook names here if you happen to be close to a library or if you want to buy them. There's a book by DeVore, Probability and Statistics for Engineering and Sciences, which is quite a nice book. And there's also Walpole, Myers, and Wires, Probability and Statistics for Engineering and Sciences as well, and scientists. And of course, everything's going to be posted and held on Brightspace, so check that regularly. The last part of this particular PDF file is the course schedule, and we're going to try to stick to this as much as possible. But basically in week 1, we're going to talk about the introduction to the course, background descriptive statistics. That's going to be lecture number 1. That'll be like a Tuesday morning. And then the Thursday morning would be sample spaces, events, basic probability concepts, and so on and so forth. So basically Tuesday, Wednesday of each week are given by the 2 bullet points. Okay, I think that's enough for this introductory lecture. I'm going to just close this and stop recording.